G'day, I'm Neil and my handle is Wiley11. I'm just going to put my disclaimer here. Whatever I do and say on these videos is well-intentioned and well-meaning advice. I accept no liabilities whatsoever for any disclosures. If you take some advice or act on something that I'm saying on these videos, you do so entirely at your own risk. I'm doing it based on my experience. These videos are my attempt to give back to YouTube for the help and assistance that YouTube has given me. So once again, you follow along or follow advice from these videos entirely at your own risk. Okay, and if you're not happy to do that, click this off and off you go. Because this is purely my attempt to give back to YouTube, as I said, for the help and advice that I have received out of YouTube. So this is just my little attempt to give back. If you're all happy to follow along at your own risk, buckle up, sit in. Let's get into it. Hello and welcome back to part 2 of Blink Like an Arduino. Okay, when I left you, we had our MP Lab installed and we had our device connected with no errors. And what we now want to do is we want to get a 12F675 like that one and insert it in our device. So here's our device. Now you'll see that there's a notch in the chip. You can see the notch, and pin 1 is denoted by that hole. So that notch goes towards the top, and that hole is right on pin 1. Now if your device is oriented a bit different to that, you need to make sure that your pin 1 is situated at the correct place and oriented correctly in your holder, and lock it in. So I'm going to switch over cameras now to the other camera and we're going to start going forwards. We were discussing this flowchart and we decided that this is the actual Blink flowchart, which it is, and we had opened up our desktop. So here's our desktop, MP Lab version 8.92. Now at this point we haven't told the desktop to do anything. So what we're going to do is we're going to go Project Wizard. And we're going to say Next. And we're going to tell it which chip we've got. And we've got this 12F675, as you can see. Now there are literally thousands or hundreds of whatever chips, picks. There's more than this list as well. There's way more. But this is the ones that are supported within this MP Lab. So I'm not going to change that. That's already pre-selected because I did one earlier. I'm just going to say Next. And we get this step 2. Now we're in assembler. If we were doing a link file, we'd pick that. If we were doing a library, we would pick that. But we're doing assembler, so we don't have to change anything in this screen, and we leave it alone. Create new project file. What I'm going to do is browse, and I'm already set up. So I'm in my outreach folder. I've got this Blink Like an Arduino, and I'm going to call it Blink Like an Arduino. Now I'm not putting any spaces in there. Some lab IDEs don't mind the spaces, others do. For example, the Arduino I think has a problem with spaces in the file names. This one I don't think has a problem with it, but I'm not putting any spaces in there. and I'm just going to save that and go next. And at this point it's asking us, do we want to add files? Well, yes we do. Now I showed you where to find that ink file, and I'm going to go back and find it for you one more time. So here's our x86 microchip. Here it is, ASM assembler, and down in here you can start to see ink files. See all these ink files, and the one we want is a P12F 675, that one. See that? So once again, x86 program files, microchip, ASM suite, and straight there under the root directory, there it is. Now that file, because it's in ASM, ASM stands for assembler. We need to add that file. But we don't want to leave it over there. What we want to do is we want to bring it into our project. So I want it to copy. So what I'm doing is I'm clicking on this A to change it to a C. And that's going to copy it into our program directory. I'm not going to add anything else at this stage. I'm just going to say next and finish. And what that's going to do is set up our project. Here it is, blink like an Arduino. And here's our header file. It's done the include. Now that file contains all of the objects for the system 12F675. And you don't have to go and recreate all that. That's done for you. So with that file included, all you've got to do is reference that file in your program, and you will have all of that available to you. Now that said, we've got to talk about what are we doing. Well, what we're doing is we're doing this bit up here, this down to this. So we've got to start a program, and we've got to do declares and setup. And as you can see, we haven't got any source files yet. So what we need to do is go ahead and add. Now what I'm doing is I'm right clicking on that, and it's got add files. That in the documents and outreach, we have this blink like an Arduino. We want to go in there. And the file we want to do is called blink.asm. Open. Okay, that wasn't the way to do that. Let's remove that. What we'll do is we'll do it using the menu. We'll go File, Add New File to Project. That's what we're trying to do. Here we are. We're in Blink like an Arduino, and we want it to be called blink.asm. Save. So you'll notice now that we have a source file. Here it is. And we're about to start programming it. Bit of a mistake on my part. I thought you could add it there. Apparently you can only add files that are already created with that method. Otherwise, if you want to create it, you go File, Add New File to Project. Okay, so now we want to start doing our flowchart. Coming back to that, we want to start, and we want to do declares and setup. Now, I'm going to shut this camera down because there's no point you looking at me. And what we're going to do, here's one I prepared earlier. Now the first thing I'll tell you is that when you type into these desktop IDEs, sometimes if you use tabs, your code will not line up when other programs write back to the screen. So for example here, you can see stuff isn't lining up, and the reason for that is that different programs interpret tab stops differently. So I don't tend to use them. Now the problem is that when you use an IDE, Integrated Desktop Environment, that stands for, if you didn't know, it has its own way of doing tab swaps, and you know, sometimes the indents do spaces and sometimes they do tabs, and it's just a case of pot luck if you're using automatic indent. I try to turn it off. I try to space things. I'm just going to paste that in there. So let's go through what I've just taken out of my working program. What I always start with is the title of the file and the date that I designed it. Now I'm going to change this date. No, I'm not. I'm going to leave it. That's the date I designed it. I'm going to leave it like that. You can see my comments are denoted by these semicolons, right? So wherever you see a semicolon, it turns green afterwards, which denotes it as being a comment. Here's a classic example of stuff not lining up. So I'm just going to fix things on the fly as we go. So I want this out here, in fact. I want it to line up with this. And again, because this comment here is part of the comment above it, I put the semi out there so that it looks like it's okay. You know, you can read it. Now, I'm going to go through this real quick. I encourage you to visit this guy's website. This is the website I was mentioning in the previous version. If you're confused, this is another research site you can go to. This is where I've developed most of my instruction from, is from this guy. I don't know who he is, but thank you to him. I encourage you to go check that out. Blink.asm by me. Now, if I were claiming copyright, I would put the copyright symbol there so that people know right away that the copyright is claimed over this file from that date. Now, I'm not claiming copyright. I'm actually releasing it under the GNU standard license. Here I've said something about the development history of the file and what we're trying to achieve. We're trying to emulate the Blink from the Arduino using the Watchdog timer on a PIC 12F675. So immediately anyone reading that knows what I'm about. So this is a detailed description. It's a beginner's tutorial. So if I'm an advanced person and I read that and I know that I can't spell beginners, is it two N's? Beginning is two N's. Beginners. Yeah, don't know if I can spell or not. Now when you double click, see this B comes up? I double click that to try to select the word like you do in Word and WordPad and all those, and most of the other editors. In this one, it puts a breakpoint in. Make sure you don't double click. It's definitely a drag system. So that's something about this desktop, this 8.92. This is all self-explanatory. So I'm giving a very detailed description of what this program is trying to achieve. So I've set three goals. I want to emulate the Arduino, I want to conserve power, and I want to expose you to the object-oriented programming techniques. I'm not going to go deep, I'm just going to touch it. Okay, so it's not by any means the correct OOP process, but I want you to be aware that OOP is a very good thing to get into. Here's my title. This list tells the processor, tells the programmer what processor I'm actually running. And if you look at this include file, which we're going to do, you will see at the very bottom, at the very top, is that list command. And I think, yeah, so here's our list command here as well. So these lists are actually given in the file. So if you weren't using this, there would be no point in telling the processor any of that. Okay, so this would not, and you'd have to go through and make your own defines and declares. So for goodness sakes, make sure you're not reinventing the wheel. Now about this file, there are two versions of it. If you've grabbed the wrong version, instead of these semis over here, there'll be these things. And that would be the C version of this file. You do not want the C version. You definitely want to make sure you've got semicolons. If you start compiling with the C version, you're going to get all sorts of errors. Now let's talk about this. This is your compile the current window. So it only compiles whatever's changed. This is erase everything and do a complete build. And this does an export of a make file, which we're not going to worry about. So we're in debug mode. We haven't set up our programmer. Let's set that up. We want to go programmer, select programmer, and here it's got none. We want to use our picket 3. Okay, it's warning us that if we've put 5 volts out to a 3.3 volt device, we're going to blow the device up. Now, at the moment, you can see here, there's nothing active on the chip. This is our chip control, and there's nothing happening, and we've got to enable that. So we've got to go into settings, and you see this power tab. We need to enable it, and this is our 5 volts to 3 volts thing. Now I'm happy to put out 5 volts. That's fine, because our data sheet tells us that our chip can handle 5 volts. Now over here in our picket 3, you can see this red error message, right? And whenever you see that, that means that this is not set. So if you set that, just hit the OK button, you'll get your warning about the 3.3 volt device, and you're going to say OK. And it's read the device and it's returned this serial number. Now what that means is that this is the original chip. This is a binary number. The B stands for binary. So don't be confused by that. But if you had revision 1, if you have 1.0, it'll be revision 2. If you have 1.1, it'll be revision 3, etc., etc., etc. So that's a binary number. And you'll notice that we don't have any errors. Now right now, we've done these configs and error level stuff, and we should be able to do a build. Let's just do a build. And see, it's swept over to build. Now I always select relocatable the default. I don't really understand that, and I'm not going to bother. But I know it just works. Now I've got build failed. Error. Doesn't. Oh, I'll tell you what we haven't done. We haven't told it to end. So what we should have done was tell it to end. Okay, so with every assembler system, you need to tell it that it needs to finish somewhere. So there's our end command. Now if we do our build, we'll be okay. Build succeeded. You must tell the programmer where it ends. You don't have to tell it. In fact, I didn't need to do any of this. All I needed to do was put that end in, and we would have been able to build. Now I want to check that the chip is connected. So what I want to do is I want to just real quick erase the flash device. I'm going to come over to our picket tab over here in our output. You can see here. And what I want to do is erase the chip that we've just put in our holder. I'm just going to show you that. So you can see that this chip's been programmed with flash. It's pulsing, and I'm going to ask it to erase it. And you saw my write happen there, and over here you can see that the erase of that chip is complete. Alright, so we've now got a blank chip there, and we're okay to do anything we like with it. Now let's talk about the 12F675 for a minute. By default, it's a comparator. So the default factory setting for this is set up as a comparator. We've got to set all the comparator stuff off, and we've got to set up the Watchdog timer, which we're using, to come on so that we can use it. So let's come back to our program. I'm just going to minimize this. I want to come back over here and maximize this. I don't think you need to see me. I'll just shut that down. Here's our Blink program. And you can see this config file. Well, this config file is referencing this inc file. And we're calling these methods. So we're turning our comparator off, our comparator data off. Whatever the button is getting turned off. And whatever that is getting turned on. Here's our Watchdog. It's getting turned on. We're turning that on. And we're asking it to use the internal oscillator with no clock out. So we're not sending any pulse out of the chip. So that pin 3, which is the clock out, is not being used. Here I've asked it to ignore error number 302. And here I've asked it to ignore error number 207. These are not errors, they're just warnings. So they're not actual errors, and they don't halt your program. So they do come up, but because they're warnings, I don't care. I'm happy to just let things run. Right, we're on to the next bit. We've got to do this setup thing. Let's go back to our flowchart. So we've got to do this declares and setup. We've done part of the setup. We've done the config, which is the system setup. So now we've got to do the declares. So let's do that. Let's jump in. And what we're doing here, we're not actually going to be using any special registers. And let's do all the setup. So because we're not writing out to RAM at all in this example, we're not setting up any registers, but we are setting up these variables. These are actually constants, but we're just, for ease of use, going to set them as variables. What do I do? Okay, so here we are. Here's our variables all set up. Let's talk about them. LED on is going to be 01H. This is hexadecimal notation. So 01 is actually 1. 04 is 4. If this was 10, this would be 16, right? If this was 40, it would be whatever 4 16s are. 4 6s are 20, it would be 64. This is decimal notation, so I'm saying use GPIO number 1, LED pin. And when I set up the pin, I also have got to set up the register to tell it that pin 1 is an output. So these registers, these are the GPIO pins, and that starts from 0, 1, 2, 3, as you can see here, back to 5. They counts from the right. So if it's a 1, it's an input. And by default, they're inputs, and they should stay as inputs. In case you hook a wire up to it and it puts power to it, you're not putting power to an output, you know. That can do serious damage to your chip. So leave them as inputs. So make it an output, and that's it. That's all we're doing. So this is our Watchdog timer settings. This is self-explanatory. 18 milliseconds is approximately the default value of what they call the pre-scaler, and that's multiplied by 2 to the power of whatever your post-scaler value is. So this is 18 by 2, which equals 36. This one is 18 by 2 to the 4, which is 18 by 16, which is around for about half a second. Ish. I've said ish. This is my LED on GPIO 1. This is my setup in-outs. And if I'd set up on pin 0, I would have had to change this string here to that. So that's all that's saying. This is setting up. So we're in the setup. So we're organising the compiler to start at 0. This will be common to every piece of code you ever write in assembler. You will have to tell it where to start compiling. This is turning the comparator off. This is the comparator register, which is defined up here in this file. GPIO is also defined in this file, and we are clearing it. So we're saying please put zeros everywhere so that we don't send any value out inadvertently. So if we're attached to, say, a machine gun or something, we're not going to start that thing firing as soon as we turn a chip on, right? We want it to be off. We want to point at the special RAM so that we can reference these registers. So we're turning it from the RAM into basically the ROM, or the higher memory registers. We want to turn off analog, so we're clearing it. We don't want any analog in our project. We are moving into the right area our in-out string. Here it is here. So we're shifting that into our Trizio, which is our tri-state I/O registers, and they're defined in this area up here. Right? So all the tri-state means is that we want to define things as inputs or outputs. That's all it's doing. And then we're setting our status back to bank 0. Cool. Now, if we compile this, we should still get an OK. Here we go, build succeeded. Okay, we haven't told it to do anything. All we've told it is where everything is. Alright, so now we've done, it's a good idea once you've done your setup to do this, to see if you've forgotten anything or if anything's missing from this. That's a very good practice, is to do regular compiles, because if you've made a mistake, it's better to find it when you've done 10, 15 minutes coding to if you've done 2 to 3 hours of coding. Our compile is done, and what we now want to do is we want to go back to our flowchart. This is our plan. We've done all this. We're now doing this bit. Now essentially, this whole thing here is a method, right? And in object-oriented programming, you want to try to encapsulate methods, and this method we're going to call flash. So I'm just going to open up our thing, and here we're just going to say this thing is called flash. So what we're doing is we're going round and round and round and round and round in this flash thing. So let's do that. Here's one I prepared earlier. Now my main loop is easy to identify, because I always call it main loop. You want to be consistent. When you start doing things, if you do things consistently, people get to know the way you code, and if you got to give this to somebody else, if you know, they can follow it. It's all lined up, it's all neat, everything's where it should be, and people can follow it. Alright, so here's our main loop. That should all work, right? Let's try to build, it should know what to do. We've told it to flash, and we've told it to go back to there and go again, right? So let's do that. What's going to happen? We've got a 50-50 shot. Let's go. Oops, there's something majorly wrong with that. Now let's find out. See this error? When I double click that, it takes me exactly to where it is. See that? So I double clicked on that, and it took me over here. And what it's telling you is that it doesn't understand flash. Right? Symbol not previously defined, flash. It doesn't understand. What do you mean flash? Well, we didn't tell it what a flash was. I double clicked. Remember the break? Just remember, if they're set, your code's going to stop somewhere, and it just confuses the living crap out of you when you're a beginner. Well, we haven't told it what a flash is, so we need to do that. Now, I want to pause and I want to talk about the difference between call and GoTo. When you use call, the system remembers where it was. So it'll do this and then come back here and execute the next thing. When you say GoTo, it doesn't remember. So it'll go do that, and it won't remember anything before that event. So it won't know it was there. It won't know where it was. So that's the main difference between call and GoTo. And that illustrates it beautifully. So let's tell it what flash means. What do you reckon, folks? If we tell it what flash means, will it work? Well, let's have a go. Here's one I prepared earlier. Now you'll notice that I've described my code. Again, I didn't just write that method. I told the system what I'm trying to do. Turns the LED, then turns it off, and then sets the sleep on the LED to the off time. So it turns on the LED. Hang on, maybe it doesn't do that. It's got this thing here. So it's doing a few more things than our flowchart said. Let's go back to our flowchart and see if we can follow it. Turn on the LED. Well, there it is. We've turned it on. Turn on the LED. Tick. We've done that. Sleep. Well, there's no sleep in there. So instead of sleep, we've done this stuff. We've done this status thing, we've done an LED on, and we've done a set the watchdog. Turn the LED off. Yep, we've done that. Sleep with. Here we've done a BCF. Now let's talk about this BSF and BCF. BSF is bit set. Bit set. Now bit set changes the value to a 1. So I've said go to the GPIO register LED pin. So back up here, LED pin was bit 1, not bit 0, bit 1. So it starts at 0. So 0, 1, 0, 1. So it's setting this bit here. And it's setting it, remember we did a clear up here, we put everything to 0, GPIO 0. That cleared it all out. So now what we want to do is set it to a 1. So we're turning it on. Here we are setting the pointer to the upper register, and we are moving the value of LED on, this one, 01H, into our right area. And then we're asking it to do a set WDT. Well, I don't think the system knows anything about that WDT thing. In fact, I'm sure it doesn't, because if I try to build this, which I'm not sure where my build button went, we're going to get another error, build failed. The reason it failed is it's got no idea what that is. Well, let's go give it the set WDT. Let's give it the last bit. Obviously, this thing here and this thing here, we've done some change. So this flowchart doesn't hold anymore. It doesn't hold water. We've changed it. So wrong and wrong. So because it's wrong, we might need to go think about what we're trying to achieve. Don't save that. And as you saw, here's one I prepared earlier. We've done a fair bit more stuff. So what we've done is we've combined these into a thing called set Watchdog. And we've done the same thing here. So what we've actually done is we've moved LED on and passed it down to the Watchdog. So that's passing all of this onto our Watchdog. Right? So we've passed in the LED on value and called it. And down here we've passed in the LED off value and called it. BCF is bit clear. So this, when you say BCF, you're clearing it to a 0. So that's the turn off bit. So that works. This is the turn on bit. So whenever you do a BSF, you should see, when you're setting a pointer, you should see a BCF. But in our code, our BSF is here, but our BCF doesn't turn off this status. See? And that's because we're doing the BCF. We handled that in this subroutine. So let's go get that and let's talk about it. Oh. Now everything should compile, shouldn't it? Well, it will. I'll tell you it will. There we go. We got everything we need to make some things happen. Remember I told you when you use call, it goes back? Well, this return tells it to go back to where you were. That's what that does. So when you got that return, see you later. Out of here. So return, go back where you were. Sleep, well, that's self-explanatory. It puts the processor to sleep. So here's our BCF here, right? So we set it there and we cleared it after we've moved that value that we passed into that register. Then we've activated the sleep, the what you were. All right, I'm just getting interrupted by messages. I think it's time to wrap up. Basically, we're very close to a finished product. We've got our revised system here. So we're going to keep this documented. We're following this flowchart. Our flash is now a one big subroutine, which has it has its own method. So flash is a subroutine with a main method and a sub method, right? So that's our object. LED is the object. So here it is up here, and it has two states, on and off. It has also an output pin. So that's defining the LED there. So that's our object defined. This is our setup for the system. This is our actual program with our method call, flash, which has a sub method or subroutine called set the watchdog. So there you go. And now what I'm going to do is I'm going to turn the camera back on right quick. And I'm going to write that out to the chip. Oh, I didn't set that to release. You need to set that to release in order to write to the chip, but it'll warn you. And there you go. And there it's blinking nice and slow. Yeah, lovely slow blink every half second or so. 1 and 2, no, nearly 2 seconds. 18 by 16, almost 2 seconds. 20 by 20, 4,000. Who knows? That's a nice slow blink. Blink on, blink off. Blink on, 2, 3. Blink off, 1, 2, 3. 1, 2, 3. What I'm going to do, is change real quick. Just go back to my blink window. Right, and change the time. So instead of that being 04, I want to change that to 02. And what that should do is pulse this thing on and off really quickly. Let me write that. I didn't do a build, did I? Sorry, got to build it first, Neil. Right, now you can write it to the chip. And there it is pulsing. See that? So we're definitely manipulating that chip. There's nothing default about it. We're definitely doing all of that with our code. And at that point, that's a good point to wrap this video up. If you go to page 70 of this document, you're going to find the instruction set. I asked it to go to page 70 and it went to page 69. So here's the instruction set. And if you familiarize yourself with all of these instructions, you'll be able to program the chips, with next to no effort. So I would recommend you go to page 70 of the 12F675 data sheet. And down here there's an explanation that tells you what each of these commands will do. So remember I told you BCF puts zeros in, right? So this is the, you can actually get it right down to a register and a bit. F means bit clear register, the register name and whatever bit. Now if that's left blank, it'll do the whole register. So it's saying it will put a 0 for every bit that you nominate. So you can do it bit by bit or you can do the whole register. Alright, bit B and register F is cleared. So if you leave the B off that, it'll do the lot. No, it won't. It'll fail. My mistake. CRLF will clear the whole register. So here, this is the one I was thinking of. So if you only want to do one bit, you use BCF. I was giving you a bum steer there. BCF is to clear one bit at a time, right? Counting from the right. So bit 0 is over on the right, and bit 7's on the left. Okay, bits 0 to 7, which is 8 bits. If you want to clear the lot, you use this one, CRLF, which clears the lot out. Okay? There are obviously 128 registers that this can be acted upon. CLRW clears the right register. The W register is cleared. The W is the right register. It's a temporary right register. Clear WDT will clear the Watchdog timer. Now, interestingly, it says it also resets the prescaler. So be very careful about using this one, because you might set the prescaler to something else. Anyway, you'll get the gist of this. Clear W clears out the write register. It's actually a good idea to clear it before you write to it, because you can end up with unexpected results. So you should do a CLRW before you do a MOVW. It's always good practice to do that, and I didn't do that in my example, so for that I apologise. But you should always clear out the write register before you write to it, because you don't know what was left over from the previous instruction, and there might be something that you haven't actively intended to write up in the upper register that will write to your area, to your chip, and you might end up with the wrong result. All right, that's for you to take your time over and make yourself familiar with. Okay, so I want to wrap it up there. I want you to support my company, nightglowmanufacturing.com, so that I can continue to live and make videos and, continue to get going forwards. If you made it to this point, congratulations. That's actually a pretty decent result for, as a beginner. We've touched on some object-oriented programming. That's not by any means a full breakdown of how you would do this with a full object-oriented model, but we've done a high-level object system. We could do a more detailed one where we would break out the objects and we would plot the relationships between the objects and the methods, and that's a flow diagram. So we've done a system flow chart, but we haven't done sort of the object models, which would be the next step in object-oriented program. We'd actually have to do an object model and plot the properties of each object and the methods and the sets and gets and lets and all the rest of that. We've just done this at a very high level and we've touched on it. And if you want to get into OOP, object-oriented programming, I recommend you do, because it's about building an object and being able to pick it up and put it in a different project and it will just work. That's what it's about. And you can recycle all of the code for that object by just picking it up and plugging it in. So it's plug and play. Now it does create more code. It does that because you've got the same standard for every object. Every object is consistently built. And if you call some object which says set color, then every time you call set color, that method will require some object properties which says which object and what color, and it will go away and set the color for that object. And if you plug a new object in and it hasn't got a thing called color, well, it won't know what to set. So you've got to be consistent. Every time you build things, do it the same way. Be consistent. And if you're consistent, even if you're consistently wrong, then fixing the error it should be a simple matter of going back through the archive and changing whatever's in the archive to an upgrade. Being consistent is good, always. Being consistent in programming is always good. So as a beginner, I want to encourage you to write down your plan. I want you to think about the relationships between the things that are in what you wrote down, and draw up a little flowchart that you're aiming at, that you want to get to, so that you've got your main program loop going round and round and round. This thing, it's just got to be consistent. Well, once again, support my company, Nightglow Manufacturing. Make good decisions and do good things. nightglowmanufacturing.com. You can actually buy a blinking light, which is based on this project. Good decisions, good things. Comment, subscribe, like. Do the things that get me noticed, and of course more people get to see and hear about this. And thank you for tuning in, and I hope you got something out of it. Be good. Catch you next video.